In manufacturing, inputs are rarely rigid. A commercial bakery might swap Georgia pecans for Florida pecans based on seasonal availability. A factory foreman might cover a weekend shift by substituting highly skilled senior technicians for junior operators. When managers make these substitutions, the traditional standard efficiency variance falls short as a diagnostic tool. The flaw is mathematical. A standard efficiency variance calculates the total difference in quantity used, but it cannot tell you if that cost difference came from altering the proportion of the inputs or simply consuming a greater total volume of materials. To solve this, cost accountants apply mathematical decomposition to split the standard variance into two independent variables. The first component is the mix variance. This measures the specific financial impact of altering the recipe, using a different proportion of cheap versus expensive inputs. The second component is the yield variance. This isolates the financial impact of the physical volume consumed, whether the process required more or fewer total inputs than budgeted to create the final output. Together, they form a complete picture. The parent quantity, or efficiency variance, splits cleanly into these two parallel child nodes. We are going to construct the exact mechanical framework required to isolate and calculate these two variables. Because without separating mix from yield, controllers cannot accurately diagnose whether a massive cost overrun was caused by an aggressive purchasing decision or excessive physical waste on the factory floor. To calculate the isolated impact of a substitution, the framework relies on two precise weighted average prices to act as mathematical pivot points. We define these as the standard mix at standard prices, or SMSP, and the actual mix at standard prices, or AMSP. Consider a retail store budgeting labor for the upcoming month.
To set a baseline, management establishes an expected mix of employee hours. This table outlines the standard mix. The store plans to use 200 manager, 800 associate, and 600 warehouse hours. By dividing the total standard cost of $20,400 by 1,600 total hours, we isolate the baseline rate. The SMSP is exactly $12.75 per hour. Fast forward to month end. Operations rarely run precisely to plan, and the actual hours worked by different staff tiers deviate from the budget. The actual hours logged here create a completely new mix, while holding the standard wage constant. Dividing the actual total cost of $19,880 by 1,500 actual total hours yields the second pivot point, an AMSP of $13.25 per hour. Comparing the two averages reveals the substitution effect. The store utilized a higher proportion of expensive manager hours relative to the cheaper warehouse hours, driving the average hourly cost upward. Finding the difference between the SMSP and the AMSP is the exact mechanism that isolates the pricing impact of substituting one labor tier for another. With these weighted averages established, we can calculate the exact dollar value of the substitution. The mix variance equals the actual total quantity multiplied by the difference between the standard mix price and the actual mix price. The formula takes this variance in our weighted averages and scales it by the actual total inputs consumed.
Let's apply this to direct materials, using a gasoline additive produced by Mac Fuels. This right-hand table displays the current period's data. At the bottom of the quantity used column, the actual total quantity consumed is 84,420 liters. The left-hand table provides standard quantities and costs required to derive our baseline standard and actual mix prices. By plugging the actual total quantity, the standard mix price, and the actual mix price into our equation, we generate a specific dollar amount for the variance. The interpretation is straightforward. If the actual mix relies heavily on lower-priced inputs compared to the budget, the average cost drops and the variance is favorable. If more expensive inputs are substituted in, the variance is unfavorable. The mix variance assigns a precise dollar figure to the decision of substituting chemical grades, entirely independent of the total volume of chemicals used. To analyze pure volume efficiency, we calculate the yield variance. This asks a different question. Regardless of the mix of inputs, did the process consume more or less total volume than allowed? The yield variance equals the difference between standard total quantity and actual total quantity multiplied by the standard mix price. It measures the physical volume difference between what was allowed and used while holding standard mix price constant. We can observe this in a firm mixing materials A and B. The firm produced 25,000 finished units.
Multiplying these by the standard allowances of 4 ounces for A and 6 ounces for B calculates the standard total quantity allowed. We contrast this against the actual usage reported, 105,000 ounces of A and 145,000 ounces of B. We multiply the total volume difference by our baseline standard mix price to find the final yield variance in dollars. The yield variance successfully strips away the pricing effects of substituting materials to reveal pure operational efficiency on the production line. These isolated calculations are two halves of a single economic reality. Mathematically, the sum of the mix variance and the yield variance precisely equals the total efficiency variance. This relationship provides immense diagnostic value, allowing management to identify hidden operational trade-offs. Consider a scenario where a purchasing manager introduces a cheaper, lower-grade raw material into an industrial refining process. Substituting this cheaper material mechanically generates a highly favorable mix variance. On paper, the purchasing department has saved money. However, these lower-grade inputs often perform poorly during actual manufacturing, requiring excessive rework or generating substantial scrap material. That physical waste drives a severely unfavorable yield variance. The factory consumes significantly more total volume to produce the required output, frequently wiping out the initial savings from the cheaper mix. If the company relied solely on a traditional combined efficiency variance, these two forces would net against each other, masking the root cause of the cost overrun. Decomposing variances into mix and yield exposes the true financial impact of substitution decisions. It provides the exact data required to correct systemic operational issues rather than chasing shadows.